Cloud-native AI and microservices. Containerizing agents and scaling inference, Chapter 1, Foundations of Cloud-native AI, from Monoliths to Microservices. The theoretical foundation for containerizing AI agents and orchestrating them within a cloud-native ecosystem rests on a fundamental shift from monolithic application design to distributed, resilient, and observable systems. In the context of AI agents, autonomous entities that perceive, reason, and act, this shift is not merely a deployment convenience but a necessity for scalability and reliability. To understand this, we must first dissect the anatomy of an AI agent in a production environment and map it to the primitives provided by modern container orchestration. Turning our attention to the agent as a microservice, deconstructing the runtime. An AI agent is not a static script, it is a dynamic process. At its core, an agent consists of three distinct layers: the model layer, the brain, typically a large language model or a specialized vision model; the orchestration layer, the cognitive architecture, handling memory, planning, and tool usage; and the interface layer, the API or event stream connecting it to the outside world. In a traditional deployment, these layers are often tightly coupled within a single Python process. However, this creates a dependency hell where specific versions of transformers, torch, and OpenAI libraries conflict. Furthermore, the resource requirements for the model layer, GPU memory, high bandwidth interconnects, are vastly different from the orchestration layer, CPU-intensive, state management. The real-world analogy: the professional kitchen. Imagine a high-end restaurant kitchen. The model layer is the specialized station, say, the sous vide machine or the wok station. It requires specific equipment, high heat, and precise timing. The orchestration layer is the head chef, who doesn't cook every dish but directs the flow, checks quality, and decides when to use which tool. The interface layer is the waiter taking orders. In a monolithic design, the head chef is also washing the dishes and managing the inventory. If the wok station overheats, GPU memory exhaustion, the entire kitchen halts. By containerizing, we separate the stations. The sous vide machine, model, is in its own insulated box; container, the chef, orchestration, is at the pass; and the waiter, interface, is at the door. If the wok station needs more power, we don't rebuild the kitchen, we just add another identical wok station, horizontal scaling. Moving on to why C# in the AI ecosystem. While Python dominates AI research, C# provides the structural rigor required for enterprise-grade production systems. C# static typing, async/await patterns, and robust dependency injection frameworks align perfectly with the requirements of distributed systems. Consider the interface layer. In a multi-agent system, agents must communicate. If we rely on dynamic typing, a change in the message schema between agent A and agent B might only be caught at runtime, potentially causing a cascading failure in a complex workflow. C# enforces contracts at compile time. Critical concept reference: this mirrors the principles of domain-driven design, DDD, introduced in Book 2, Architectural Patterns. In DDD, we define bounded contexts to isolate domain logic. In this chapter, we treat each agent as a bounded context. C#'s record types are essential here. They provide immutable data structures that represent the state or messages of an agent, ensuring thread safety when agents operate concurrently. I am going to explain the overall purpose of this code. This is a simple cloud-native microservice built with ASP.NET Core. Its logic is to accept text data via an HTTP POST request, run a mock sentiment analysis, as a placeholder for a real AI model, and return the result as JSON. We start by importing the essential ASP.NET Core framework components to build the web application and handle JSON serialization. Now, let's look at the data structures. These are the POCOs, plain old CLR objects, that define the contract for our API. The analysis request class represents the incoming data from the client, and the analysis result class defines what we will send back. Notice how the JSON property name attributes at lines 14 and 20 ensure the JSON keys match our C# property names. Look at line 15 here. The required keyword ensures that the text property must be provided when creating an instance of analysis request. This is a modern C# feature that helps enforce data integrity at the application level before we even start processing the request. This is the analysis result class. It holds the sentiment, a confidence score, and a timestamp. In a real-world scenario, this structure would be defined by your business requirements. See at line 21 where we set a default value for sentiment. This is a good practice to avoid null reference exceptions. Here we define the inference engine interface. This is a crucial part of our design. By using an interface, we decouple our API logic from the specific implementation of the AI model. This allows us to easily swap the mock inference engine for a real one, like one using ONNX runtime, later without changing the API endpoint code. Now we implement the mock inference engine. For this example, it's a placeholder. In a real microservice, this class would load a trained model file. Notice at line 43 that we are injecting an iLogger. This is a core concept in cloud-native apps. We use dependency injection to get logging services, which helps us monitor the application's behavior in production. Let's examine the analyze method's logic. It's a simple simulation. It checks for keywords like good or bad to determine sentiment. In a real AI inference engine, this step would involve converting text to vectors and running a complex mathematical model. This mock logic is just to demonstrate the flow of data through the service. Notice how the confidence score is set. In this mock version, it's either 0.5, neutral, or 0.95, for positive/negative. In a real AI model, the confidence score is a probability output from the model itself, representing how certain the model is about its prediction. Finally, the method constructs and returns a new analysis result object. The processStat property is set to datetime.utc-now. This is important for cloud-native applications to track when the inference was performed, especially if you are dealing with event sourcing or auditing. We are now at the program class, which is the main entry point for the application. The web application.createBuilder method at line 93 initializes a new instance of the web host builder. This is the starting point for configuring our cloud-native microservice. Look at line 99. We are using add singleton to register our iInference engine. This means that a single instance of mock inference engine will be created and shared across all requests. This is efficient for stateless services. Remember that use routing is used later to match incoming requests to the correct endpoint handlers. Here we configure logging. We are adding console and debug output. In a real cloud deployment, like Azure Container Apps or Kubernetes, you would typically send logs to a centralized service like Azure Monitor or Seek. This configuration is essential for debugging and observability. At line 108, we call builder build to create the web application instance. This finalizes the configuration and prepares the application to handle requests. Immediately after, at line 112, we define our API endpoint using mappost for the /analyze route. Inside the endpoint handler, we start by deserializing the request body. See at line 117 where we use JSON serializer.deserializeAsync. We also perform basic validation at lines 119 to 124. If the request is invalid, we immediately return a 400 bad request status code, which is a standard practice for RESTful APIs. The core logic is executed at line 127. We call the analyze method on the injected iInference engine. The result is then serialized back to JSON and written to the response body. Notice how we set the content type to application/JSON at line 130 to inform the client about the response format. This is our global error handling block. If any exception occurs during the request processing, we catch it here. We set the status code to 500, internal server error, and return a generic error message. In a production system, you would log the detailed exception and avoid exposing internal details to the client. Finally, at line 143, we call app_run. This starts the Kestrel web server and begins listening for incoming HTTP requests. This line is what makes the application run and serve our sentiment analysis API to the world. Turning our attention to Dockerfile, containerization. To make this microservice cloud native, we must package it into a container. Below is a Dockerfile to build the image. This Dockerfile builds a container image for an ASP.NET Core application called Agent Service. It uses a multi-stage build process. First, it uses the .NET 8 SDK to restore dependencies, copy source code, and build the application in release mode. Notice how the build stage creates a specific directory for the output. This approach ensures the final image is optimized and smaller by separating the build environment from the runtime environment. This section defines a new stage named publish based on the previous build stage. The command runs .NET publish to create a ready-to-run output package. Look at the O flag which specifies the output directory as /app/publish. This step prepares the compiled application for the final runtime image. Here we define the final runtime image using the ASP.NET Core runtime image, which is smaller than the SDK image. The workdir sets the working directory to /app. See at line 24 where the copy from =publish command copies only the published application files from the publish stage into this final image. This is crucial for keeping the production image lean. The last two lines configure the container runtime. Line 27 exposes port 80, which is the default port for ASP.NET Core applications inside containers. Line 30 sets the entry pin to run the agentservice.dll file using the .NET command. Remember that this command is what the container will execute when it starts launching your application. Turning our attention to common pitfalls. 1. Statefulness in stateless services. Mistake: storing data in static variables or class fields within the inference engine or controller, e.g., private static list to string underscore cache equals new, winky face. Consequence: in Kubernetes, you typically run multiple replicas, pods, of a microservice. If a user's request hits pod A, and their next request hits pod B, the state stored in pod A is inaccessible to pod B. This leads to inconsistent behavior and data loss. Solution: treat microservices as stateless. Store state in external services like Redis, for caching, or a database. 2. Ignoring graceful shutdown. Mistake: not handling SIGTERM signals properly. Consequence: when Kubernetes performs a rolling update or scales down a deployment, it sends a SIGTERM signal to the pod. If the application ignores this and immediately terminates, in-flight inference requests might be dropped, leading to errors for users. Solution: ASP.NET Core handles this reasonably well by default, completing ongoing requests, but for long-running inference jobs, you should register iHost application lifetime listeners to pause accepting new requests and finish current ones before shutting down. 3. Large container images. Mistake: using the SDK image as the final production image. Consequence: large images take longer to pull from the registry to the Kubernetes nodes, slowing down scaling events, auto-scaling. They also increase the security risk by including build tools. Solution: always use multi-stage builds as shown in the example, ensuring the final image contains only the runtime and your application artifacts. Thank you for your attention. This lesson is excerpted from Volume 7 of the C# and AI Masterclass ebook series and from the volume Cloud Native AI and Microservices, Containerizing Agents and Scaling Inference. You can find all the details here. https://github.com/edgarmilvoos/C# programming series. The ebook also includes diagrams, advanced examples, and 5 exercises with solutions for every chapter. There are 26 chapters. If printed, it would exceed 600 pages. Subscribe to the channel to watch more videos. I look forward to seeing you in the next lesson.